Today, who the first person was the name for him, so he apparently but he donated to both of them. Yeah, and it makes sense, and his wife. Was very into and there's like a hospital next to me. It's so very popular. So everybody knows. He might have been. Is that Sparta? Public Sparta, like there's also their meals. I'm like, this is a trend. Yeah, like Vanderbilt. Because there's like a Vanderbilt clinic near me, and then there's Vanderbilt University.
Okay. Let's hope so. Yeah. Okay, sorry about that. We got thrown off by previous class. Okay, so let's get going. Today we're going to be talking about probability with discrete random variables. Before we do that, I have to repeat what I said last time because this is streaming, but it hasn't changed. Okay, so the goals for today are to start learning something about probability with some degree of rigor, much less rigor than what a mathematician would say or anything like that. But this is what distinguishes primarily people who might have been statistics major as undergrad versus people who took some social science program as an undergrad. With stat majors, they would be required to take a whole semester class like this. And so they get comfortable with it whether they like it or not. In contrast, social science usually tries to skip this more foundational stuff and then goes directly to how to operate the computer to do a bunch of things, but that's not going to be sufficient for us. And so we want to start this today, build on it every week this semester. We're also today going to compare and contrast what I call the ancient and modern ways to compute things with Bayes' rule. Ancient goes up till 1989, at which the calculations could be done with a pen or a slide rule or adding machine or pocket calculator, something like that, depending on which decade you were in contrast to 1990 and afterwards, which started the modern approach to Bayesian inference and computation more generally, where we're going to use R to do a lot of computer simulations, which is more general. The ancient way can only really be done for a small subset of problems, but when the ancient way works, it's going to coincide with the modern way, and that's going to be true today. We're also going to compare and contrast the Bayesian approach to quantitative methods with other approaches, in particular the frequentist one. So that's what we're doing today. And to start with, let's define random variables, which is the basic object in probability. But before we can get to random variables, we have to define what it means, just mathematically, a function. So a function is a rule that uniquely maps each element of an input set to some element of an output set. So if we have the very famous function e, it's a number 2.78 approximately, raised to the power x, that's going to map all real numbers that x could be to non-negative real numbers. So e raised to the power of anything is going to be non-negative. So we have a mapping from all real numbers set, that's the input set, to non-negative real numbers, that's the output set. Okay, so if that's the definition of a function, what's the definition of a random variable? Well, a random variable is a special type of function. It's going to be a mapping from the input set, which is also known as the sample space, and it is often denoted with this Greek letter uppercase omega. That's the input set. A function is a mapping from the input set to some subset of the real numbers. That's going to be its output set. And what is this blocking the way? Subset of real numbers is the output set. And what distinguishes the probability functions is they're going to have their rule that defines the mapping as some probability-based rule. And so in the case where the sample space omega is discrete, which it is today, with a finite number of elements, we can simply enumerate an equivalent number of probabilities to say what is the probability for each element in the input set. So everybody, if you don't have your R opened up already, open it to RStudio, and let's execute this line of code here. So we're going to call the sample function. The input set here is the integers between 1 to 6. So we can think of this as like rolling a die. So it has 6 sides. So the side that's face up can be any number, 1, 2, 3, 4, 5, or 6. We want to take a sample, in this case, of size 1. And we're going to specify the probability of each side of the die coming up to be 1/6. So we're going to call the rep function to repeat 1/6 6 times. So every face of our die has the equivalent probability to be face up when we roll it in R. May want to move to higher ground. I don't know if, okay. So one thing that is confusing, justifiably, we don't want to conflate a realization of a random variable, which is a number, with the function that generates it. And there's a convention, albeit a confusing one, where a capital letter like X indicates a random variable, a function, a process, and its lowercase counterpart, little x, indicates a realization of that random variable, a number. So the process is like rolling a die. The number is the face of the die that is up. And we use capital X and lowercase x to distinguish between those. That goes back to the day when they were typing this on a typewriter. And so they had no real way to like distinguish these things. So they invented this capital lowercase distinction. Another way you can see it is if you look at the R code, well, everything to the right of the assignment arrow, that's a function call. So that would be like the random variable. That would be the capital X, the process, the function call in order to sample from the faces of a die. And then the thing to the left of the arrow is the realization of that process. Roll is going to be some number, like 2, depending on what you got. All right? So everybody understand that and can see that. Okay? Good. Okay. So rolling a die, example of a random variable. But it's not a very interesting one, and it's not a very rich one. Like the video on the syllabus for this week, you know, flipping coins and rolling die, it's not really good for learning because it's too simplistic. And so what we are going to talk about is not rolling a die, but rolling a bowling ball, which you might say, like, what does that have to do with social science? Well, Bob Putnam wrote that book, but other than that, not much. But bowling is the simplest example that is rich enough to illustrate almost all the probability concepts that we want to talk about. So that's what we're going to go with. So bowling is a very simple game. Each frame of bowling starts with n equal 10 pins upright, and you get 2 rolls per frame to knock down as many pins as you can. That's it. You've probably, some of you maybe have been bowling
Here's
before.
Kyle Kroll.
Here is a
Tom
video
said you've bowled with
of
him
bowling.
quite a bit.
This guy
Yeah,
on the
man,
right
bowled
is
at,
making his
San
first
Diego
roll
University.
now. Rolls, hits the pins.
Oh, what a
8
bad
fall
break.
down.
7-10.
to
Yeah,
stay
awful.
That's very easy to have happen here, though, on this oil pattern.
I had one
Apparently that's
today,
easy
yeah.
to have happen on this oil pattern. He's now got two
Now
pins
let's
left
see
up,
if
and
he
he's
can,
going to make
give it a
his
run.
second roll. Over there was a
It's pretty
strike.
hard. I give him a shot to make it.
Oh, he made it! Oh my God! He picked the
It's a
710. It's almost
spare.
like we knew it was coming.
Taking down all 10 pins.
Wow! Congratulations. That was cool. I don't know how many times that's happened here.
One tonight.
One tonight. Nice job.
At least
Kyle
only one
Kroll.
on camera.
Okay, that's all you have to understand about bowling.
Now let's see if he.
Shut up. So, what would the sample space omega be for the number of pins knocked down on the first roll of a frame of bowling?
0 to 10.
0 to 10, the integers. Right. So you can get 0 if you go too far to one side. All right. And so, okay, just brief one sentence review on logarithms. If you have some number b, which is the base, raised to a power p, if that is equal to some number y, then the logarithm base b of y is the function that yields p. So logarithms are like the inverse operation to exponentiation. And let's let the probability of knocking down x out of n pins be this expression, which is actually something called Benford's law. That's not super important, but you can click on the Wikipedia link later if you want to. The probability of knocking down x out of n pins is going to be given by a function, logarithm base n plus 2, of the argument 1 plus 1 over n plus 1 minus x. Now that seems like a weird looking function for a number of reasons. First of all, most of the time, like every time after first couple of weeks when I talk about logarithms, I'm going to be referring to natural logarithms, most specifically base e logarithms. Those are the most common in statistics. But for today, I'm talking about integer logarithms, but not necessarily 10, which is like the other most common logarithm you see. So this looks like a weird function, and it is, but it gives us something reasonable for probabilities. So we got a little bit thrown off kilter. So if you get this URL and source it into your R session, it should work. So tinyurl.com/gr5065 week 02. And if you just put that in source in quotation marks in your R session, it should grab a file off of GitHub that you can use for today. So you don't have to copy down the thing that used to be up on the slide. Did everybody get that URL? Okay. Okay, so if you do source of that URL instead of bowling.r, then it will do these 3 lines above. So PR is the function in R code given by this function in math right here. Okay? So if we're going to use the if-else function, if x is greater than n, the probability of that is 0. Can't knock down more than n pins. But if if x is less than or equal to n, then it's going to evaluate this, which is the same as that. Okay? Then we're going to define our sample space, omega, as the integers between 0 and 10. And so if you source in this URL, it will make the PR function to return the probabilities. And then instead of rolling a die, metaphorically, you can roll a bowling ball, metaphorically, by calling sample omega, size equal 1, and the probability of each of the elements of omega is given by calling the PR function on the set omega, and that has a default argument n equal 10, which is appropriate for the first roll of a frame of bowling. So let's have everybody do this last line here to draw a realization for the number of pins knocked down on the first roll of your frame, your first frame of bowling. Okay, how many have been able to successfully draw X1? All right. Fingers in the air for how many pins you knocked over. 10. Very good. 6. 10. 7. 10. Everybody.
The,
What?
the file isn't working for some of us.
Okay. If the file is not working, just quickly type in line 2. I meant the file just avoids you to have to type in line 2 and line 3, but then you should be good to go. So it's just an if else x greater than n, that's 0, and then else that logarithm business to the base n plus 2, and then you'll be able to call it on omega.
Wait, this is the link we're supposed to bring us to?
Yeah,
Okay.
if you just paste that in,
It's different than that one, but I think it comes up.
it's the same thing. Yeah, if you just copy and paste it
Yeah.
into R, that will work. Anything. It was supposed to be more automated, but then. Okay, so has everybody been able to get a roll of bowling?
It says I can't open the connection.
Eh. Can you open this in a web browser
Yes.
and then
Okay,
paste
cool.
in the code?
Okay, cool.
So I did that, and then when I the source, like the source command.
Okay, don't do the source command. Just copy and paste from this URL into your RStudio, and then you'll have the PR function, and then you can do line 6 here. So all line 5 does was like the previous 3 lines.
Yeah, I got it.
Alright, good. Okay, so instead of rolling a die, we've rolled a bowling ball. And like I was saying, this function looks weird, but if we look at the probabilities that come out of it, they look kind of plausible. In particular, they're all non-negative. So these are the probabilities if you evaluate the PR function on the omega set. And most importantly, they sum to exactly 1. So if you sum PR omega, it comes out to 1. And those are the defining characteristics of probabilities. They need to be non-negative for every element in the sample space omega, the input set. And they need to sum to 1 over all the elements in the sample space omega, which is to say something from the sample space is guaranteed to happen. Now, the probability in this case of knocking down 10 is almost 0.28, and the numbers go down from there. So this is a pretty good amateur bowler. Not like a professional bowler, but maybe someone who plays on the weekends or something like that. Okay? So there's presumably some bowler for which these probabilities are a description of, but they're admissible because they're non-negative and they add to 1. So general principle here goes beyond bowling. If your probabilities don't add up to 1, you have definitely done something wrong. If your probabilities do add up to 1, you've almost definitely done it right, because it is extremely hard to make a mistake and have the probabilities come out to be exactly 1 by accident. So some of this stuff gets challenging, but there's always ways to check whether you've done it right. And in this case, it looks right because these probabilities are non-negative and they sum to 1. Good? Okay. How would you draw x2, the realization of your second roll in the first frame of bowling? What sort of R code would you execute to accomplish that?
Sub in your first number into the n, right? So you need to update your n and your x based on whatever number you got after the first roll.
Yes. Can you be a bit more specific about what n is?
So n is the number of pins they knock down, and then x is what's left, correct?
Yes. N is the number of pins up, and x is the number of pins. That's the random variable. So what would n be for your second roll?
Well, it should be well, x it would be 10 minus a, where a is the number of pins you knock down in the first roll.
Yes. So n for the second roll is 10 minus x1. And then now we have a probability function ostensibly for the probability of knocking down any number of pins that are remaining up on our second roll of a frame of bowling. So it would look like this. We're going to sample from omega, size equal 1, prob equal PR omega, but n, it's not 10 anymore, it's 10 minus x1. So does calling probability with omega n equal 10 minus x1 yield a valid set of probabilities for you? Yes? No? Question.
Are you also factoring like in the empty spaces? Because
So we're not taking into account which 10 minus x1 pins are still up. Only the total. If we wanted to make this more complicated, we could say, well, if you have the 7 and the 10 pin still upright, that is very hard. But if you have 2 pins adjacent to each other, that is pretty easy for people who are good at bowling. We're not getting into that. So 2 is just 2. Just the count, the number. Probability omega n equal 10 minus x1, is that valid set of probabilities? How do you know when you do that? It's not like apparent, it's not obvious. But if you look at PR omega n equal 10 minus x1 in your R session, do those probabilities look valid to you? Yes?
Yeah, for the first one I got X1 I got 8, so it has 0.2 for 0 pins, 0.292 for 1 pin, 0.5 for 2 pins, and the rest are 0.
Right, so a bunch are 0, that's okay. They just need to be non-negative. But what's the other criterion we need for probabilities?
The other one.
Does it add up to 1?
Probably.
Definitely.
Yeah.
That's what makes probability, right? So these are valid, in which case this call gives you a legitimate x2 roll for your number of pins knocked down on your second roll. So for those of you who knocked down all 10 pins on your first roll of a frame of bowling, what did you get for x2?
0.
0. Why?
Because you knocked down all of the pins, so there's nothing left.
Correct. In actual bowling, the second roll doesn't even happen if you make a strike. But if you did roll the second roll, there would be no pins to knock over. So you're guaranteed to get 0. So like I was talking about last week, probability can accommodate this special case where you're absolutely sure you're going to get 0 or something like that. But we're generalizing it to, if there were some n pins up that's more than 0, the probability of knocking some of them or all of them down. Okay? So PR probability of knocking down x pins given n equal 10 minus x1 pins are upright remaining is what's known as a conditional probability because it depends on the realization of a previous random variable, in this case x1, via n being 10 minus x1. And Joe Blitzstein, who is a very popular statistics professor at Harvard, and has like 1 million people in his introductory class. There are videos on YouTube of him teaching, claims that conditioning is the soul of statistics. Or you might say conditioning is the art of statistics. What to condition on and how that changes the probabilities. So very important concept. So you've done one frame of bowling, x1, and then use the x1 as part of the n equal 10 minus x1 to knock down more pins, x2, on the second frame of bowling. So now in pairs, why don't you do 10 frames of bowling? So and keep track of the number of pins knocked down. So you get like a whole game of bowling. You pretty much need to do what you've already done 10 times. Yeah, make pairs. You can work together. Get to know your neighbor.
Yeah, okay, all right. So I think I'm using.
You know how to do it or you're saying?
I can try.
I'm trying to switch this.
Or you can make your size over here. Created like another. Yeah, because I mean, I have like those. Okay, so go to insert. Or insert X. Go to insert. Executable zone. Executable. Executable. Yeah, no.
So this is like,
So what?
this, okay, so I think we start this.
Yes, it is. And then just the experience. Yeah. Yeah.
Oh, it's mine, it's that.
Yeah.
You got it? Good job. So if you can roll once, you can use that realization for the second roll of a frame of bowling. So if you can roll once, you can roll twice. And if you can do one frame, should be able to do 10 frames, which is one game. And you can think about this, okay, if I can do one game, I could do a match between two different bowlers who are each doing one game. And if I can do one match, I could do a whole bowling tournament. Yeah.
But then how would you program for like extra frames you get if you have the stripes on it?
too complicated, but you
Which
can
one?
model what happens. Alright,
The whole game.
okay, so that's good. You did 10, I'm gonna do 10 million, which is more frames of bowling than probably anyone has ever personally done in their entire life. So you're gonna need to load up the deep, you don't have to copy this down, but using the dplyr package. So first I'm gonna set R is 10 million, which is sort of a stand-in for infinity. If you do something enough times, it's gonna pretty much match the exact calculations. And then I'm gonna make a tibble called frames that's gonna hold the results of R frames of bowling. And then on line 3 and 4, I'm going to create the first column of my tibble called x1 by sampling from omega r times. Now because r is 10 million and omega only has 11 elements, I have to say sample with replacement is true, which is to say basically every frame put the 10 pins back up the way they were. Probability is PR omega evaluated at the default value of 10. So most of y'all probably did first roll of the first frame, second roll of the first frame, first roll of the second frame, second roll of the second frame, which would be like chronologically in bowling. But I'm gonna do all the first rolls first, just at once, 10 million. And then I'm going to call the group by function. So it's going to group by the 11 possible values of x1. And within each group, it's going to do the following. Create another column with mutate, x2, by sampling with omega, size with this thing, which says just take as many draws as there are values in that group. Again, sampling with replacement. Probability is PRN equal 10 minus x1. So I have to call first here to make that a scalar, and then it can make the x2s corresponding to all the possible realizations of x1. And then if you look at it, okay, I have a tibble, basically a data frame. It's got two columns, x1 and x2. They both are integer valued. I have 10 rows here for my first 10 frames. You can see 9, 1, 9, 1, 10, 7, 10, 0, 3, 7, stuff like that. And then I have 9,999,990 more frames that I was able to do just like that. And this is kind of a precursor to what I was saying last week in terms of everything changing in 1990 with the ability to do random numbers simulations and then treat frames like a database that you can query to answer any probability related question you want because it has 10 million frames in it, which is more than adequate to answer any sort of a question. And so just sort of remember that I've got 10 million frames floating around in my R session. So let's be a little bit more specific about the syntax I was using on the previous slide. Like I said, this is a syntax that has been popularized by the dplyr package in the tidyverse, most prominently by Hadley Wickham, but it actually was borrowed from database syntax that you might be more familiar with. So anyway, this vertical bar with a greater than sign is known as the pipe, which is borrowed from like Unix in the 1970s. It passes a previously created tibble along to the next function. And so we can map, even though it wasn't really intended for this, it maps on pretty well. So the concept of a random variable is, creating a tibble and calling the resulting column x by making some call to the sample function or another function in R that generates random values. You can also do that by passing a tibble to the mutate function. Then another important concept in probability, this is vertical bar big X equal little x. This means given that the random variable x takes the value little x. And that corresponds to if you pipe a tibble and then call the filter function with the condition big X is equal to little x, it's just going to extract the rows of the tibble slash database that satisfy that condition. So it's filter in rather than filter out. Anusha?
Yeah, so this is not the same thing as what we were going over with the the random variables and realization, right? That's not what this is.
Right, so the random variable is equal to a particular realization.
Oh, okay, so it's the same thing, okay.
Okay, so then you would have a smaller data frame that just has the rows that satisfies that condition. And then a related thing is group by, which instead of conditioning on a particular x, it's going to condition on each possible value of x, and then you can do things on each group. So it sort of corresponds to the for each construct in other computer languages. And then if you want to know the probability of something via a database query, you can pipe the data frame to the summarize function, and then use this here, mean x equal whatever. So that's going to create a logical vector, trues and falses. False is counted as 0, true is counted as 1. So if you take the average of the zeros and ones, that is a proportion. It's an estimate of the probability that the random variable capital X is equal to a particular value little x. And finally, we have the count function, which is basically like group by and then set times equal to n. So n is going to be the count of the number of times that x is 0, x is 1, etc. Yields the number of observations. So this syntax has gotten very popular in recent years in R for other reasons, like dealing with data sets and stuff like that. But we can repurpose it to be very useful for learning about probability, because pretty much all we need to do is some combination of these 4 things here. Get a database, make database queries to answer the questions that we are interested in, or the questions that we are assigned to answer, in the case of bowling. So if we wanted to check our simulations, we could do like this. Pipe frames. You don't have to copy this down. But we pipe frames to the count function. So it's going to return a tibble with 11 rows, 1 for each possible thing that x1 could be. And then I'm going to mutate to create 2 more variables. One is called proportion, which is going to be equal to the number of times that each possible value for x1 occurs, divided by r. R was 10 million for me. And then I'm going to compare that to the probability that I get from evaluating my PR function on the possible values of x1. And so when I do that, I get this. So all these numbers here are the count of the number of times that this number of pins was knocked down in my database. If I divide all of those by 10 million, I get these proportions. And these proportions are almost exactly the same as the probabilities that I obtained from evaluating my PR function. Not exactly, because 10 million is a finite number, but almost exactly because 10 million is a huge number. And so we can see that these correspond rather well, which was no surprise, or it shouldn't be a surprise, because the columns of my frames tibble were generated according to my probability function. But when you call something in accordance to a probability function, and you do it on the order of 10 to the 10 million times, there's no real difference between the proportion of realizations and the analytical probabilities here. Minor difference, but not an important difference. particularly for a perspective of social science, you don't even need 4 decimal points of accuracy. 1 is usually more than adequate because your data is not going to be measured that accurately in the first place. And so that's an important background principle to this idea of everything after 1990 being done with simulations, is because we don't really need 15, 16 decimal places of accuracy in our scientific work. And so we can get by with a reasonable number of simulations and then analyze those. Questions? Questions over here, question over there, question anywhere. Alrighty. Getting more advanced. How would you compute the probability that x1 is 8 and x2 is 2 in the same frame of bowling using our database of 10 million bowling frames? What sort of R code would you use to come up with that probability of first knocking down 8 and then knocking down the remaining 2 in the second roll of the same frame of bowling? What would that R code look like? Anisha.
Would it be the last one, the last code that you showed, like the summarize?
Summarize.
Yeah, prob mean, so you would do it for x1 equals 8, comma, x2 equals 2, if I'm not mistaken?
Almost. You need a ampersand where you had a
ampersand.
comma.
Okay, not a comma.
So summarize, give it the frames database. Here I want to calculate the joint probability of x1 being 8 and x2 being 2 in the same frame of bowling. That's what the ampersand indicates. So this is a logical vector and another logical vector. Mean computes the proportion of times where that's true. And that is an estimate of the probability, comes out to be little less than 0.06. Probability of knocking down 8 on the first roll and 2 on the second. Do you have a question?
No.
No? Anybody have a question? All right. I got a question for you. How would you calculate that probability exactly, deterministically, using the PR function rather than the database of frames? So you got the PR function in your R session. How would you call that in order to give yourself the probability of knocking down 8 pins on the first roll and 2 pins on the second roll of the same frame of bowling? Yeah?
Calculate the probability from the first ball pin and then multiplied by the second one. So the first one you count how many pins knocked down, and then the second one you count how many the remaining pins knocked down, and then you just like multiply those two probabilities.
Yes. Key part of that being you multiply. All right? So just to be explicit about what that was, you take the probability of knocking down x equal 8 pins on your first roll of frame of bowling. So that's going to have 10 upright pins available to be knocked down. So that's the probability of 8 on the first roll. And you multiply by the probability of knocking down x equal 2 pins on the second roll of a frame of bowling, given that n equal 10 minus 8, otherwise known as 2 pins, are upright and available to be knocked down. But the key part there is the multiplication of 2 probabilities in order to yield the joint probability of both of those things happening. And when you do that correctly, you get a number slightly less than 0.06, very similar to what we got with the database query. This is exact, but this is the same, right? For all practical purposes. So these ancient, or maybe better, deterministic calculations that we do describe the modern process by which the frames, all 10 million of them, were simulated. All right? And when this is feasible, it's going to coincide. But pretty soon we're going to get into situations in which it's not feasible to do the ancient deterministic calculations, but it remains feasible to do the simulations. So in a manner of speaking, doing 10 million simulations is kind of wasteful when you can just multiply like two numbers together to get the right answer. But this is very general, and this, although it works today, it's not going to work for that long. All right? It's the ancient and the modern, except in the other way order. That's modern, that's ancient. Got it? There we go. Okay, so like I was saying, in R, but pretty much every computer language, the Boolean value true maps to 1 and false maps to 0 when doing arithmetic operations. And so you can see if you do operations on logical, so if the first thing is true and the second thing is true, that's resulting thing is true. If you do true and false, or false and true, or false and false, those all come out to be false. It's just using the rules of logic that Boole or Aristotle, depending on who you want to credit for, came up with. But that would be equivalent, basically, to be true multiplied by true. True multiplied, that's going to be 1. True multiplied by false is 0. False multiplied by true is 0. False multiplied by false is 0. So we have this correspondence between the AND operation and the multiplication operation if the two arguments to multiplication are restricted to be ones or zeros. And that's okay-ish for Aristotle. But what we want to do is generalize this to numbers between 0 and 1, the probabilities, and calculate the probability that two or more propositions are both true simultaneously. So we're just doing it with two things, but this generalizes to more than two. So this upside down U-shaped thing reads as AND in the logic literature, giving us what the Morin-Siegel reading refers to as the general multiplication rule, the probability that A and B happen, both, is the probability that B happens times the conditional probability that A happens given that B happens. But that is also equal to the probability that A happens times the conditional probability that B happens given that A has happened. And so this idea of multiplication of probability with a conditional probability given that the first thing happens, yielding the probability that both things happen, both A and B happen. And like I said, this can be extended to 3, 4, 5, any number of things by additional multiplications of conditional probabilities. It's part of the reason why Blitzstein says conditioning is the soul of statistics. Okay, we good so far? Case where A and B are independent of each other. This is informally speaking. If A happens, that tells me nothing about B. And if B happens, that tells me nothing about A. So if A and B are independent, then the probability of A given B simplifies to just the probability of A. It doesn't depend on B anymore. And likewise, the probability of B given A is just the probability of B. Therefore, in the special case where A and B are independent of each other, the probability of A and B is just the probability of A times the probability of B, and you don't have to worry about conditioning. So when you rolled your 10 frames of bowling, you were presumably making the implicit, albeit reasonable assumption that frame 2 is independent of frame 1, because nothing about frame 1 went into your calculation of the probabilities going, or for knocking down some number of pins on the second frame. And so according to the rules of bowling, the frames are independent of each other because they stack up in pins, 10 pins both times. Although you could make some arguments, maybe you get better practice or calibration or something like that, so which your subsequent probabilities might be higher than the previous probabilities, something like that. In that case, they wouldn't be totally independent. But anyway, it's good enough for a starting assumption for us to assume the frames are independent of each other, but the two rolls within one frame are not independent of each other, because the number of pins to be knocked down on the second roll of a frame of bowling is 10 minus the number of pins knocked down on the first roll of a frame of bowling. When I said bowling is like the simplest example that is rich enough to illustrate all the concepts, a big part of the reason why I say that is we have a very simple but explicit conditioning mechanism for the second roll depending on the first roll. Okay? All right. So don't do that, but just watch me do this. So I'm going to create a matrix that is 11 by 11 that's going to hold the joint or bivariate probabilities of knocking down X1 and X2 pins on the same frame of bowling. So I'm going to create a matrix. I'm going to fill it with zeros. It's going to have 11 rows and 11 columns. And then I'm going to do a couple of for loops like this. So for each value X1 in my set omega, again, omega is the integers between 0 and 10, I'm going to calculate the probability of knocking down X1 pins by evaluating my PR function at X1 with n equal 10. I'm going to store that locally. And then I'm going to do another inner for loop, X2, all the values between 0 and 10 minus X1. And then on line 7, I'm going to multiply the probability of knocking down X1 pins on the first roll of my frame of bowling times the conditional probability of knocking down X2 pins, given that 10 minus X1 pins are upright and available to be knocked down. General multiplication rule. Multiplying those things together gives me the probability that both happen. And I'm going to stick it into my matrix. Only thing that's a little confusing here, R starts indexing at 1 as opposed to 0, like in Python or C. So when I stick it in the matrix, I have to plus 1 the indices, so I don't like stick something into the 0th row, because the 0th row doesn't exist. Okay? So when I do that, and then I sum up over all the elements in my 11 by 11 matrix, it comes out to 1. So the probability of something happening on a frame of bowling is 1. And then the individual elements of the matrix tell me the probability of knocking down that number of X1 pins and that number of X2 pins in a frame of bowling. So a question to consider, what's the probability of knocking down 9 pins, second roll of a frame of bowling, but irrespective of what happens on the first roll, regardless of what happens on the first roll? How would you utilize the matrix, which I'm going to put up in a second, to calculate that? So here we have the matrix created by the previous code on the slide. So the row labels correspond to the number of pins knocked down on the first roll of a frame of bowling. The column labels correspond to the number of pins knocked down on the second roll of a frame of bowling. The number at the intersection of a row and a column is the probability of knocking down that number of pins on the first roll, and the column number of pins on the second roll. So the probability of knocking down 6 pins on the first roll, and 1 pin on the second roll is 0.0091. And that was done by repeated multiplications. Okay? So these numbers in black are the probability of knocking down row number of pins on the first roll and column number of pins on the second roll of the same frame of bowling. Okay? So, cognition test. Why are all these numbers in the bottom right over here 0? Nisha.
Because, like, if you knock down, like, 1 pin, for instance, like, it has to add up to 10, basically, so that was, like, my thought process, because if you go to, like, 10, 0, like, you're obviously gonna have 0 left over, because all of them are knocked. So it's just based on, like, how many pins are left, depending on, like, how many you knock.
Yes. In shorter words, you can't knock down more than 10
Yeah.
pins on one frame of bowling. So the probability of knocking down like 8 and 6 is 0. Exactly 0. Literally 0. A lot of these numbers up in the top left are small, close to 0, not literally 0. They're unlikely, but they're possible. Whereas the ones in red, impossible under the rules of bowling. Okay, back to the question that I asked on the previous slide. How would you use this matrix to tell me the probability of knocking down 9 pins, second roll, frame of bowling, irrespective of what happens on the first roll, regardless of what happens on the first roll? If I don't tell you what happens on the first roll, what would you say is the probability of knocking down 9 pins on the second roll?
You just add up the 9th column,
Mhm.
those probabilities.
So you're saying add up this and that? Why?
Because that, irrespective of what is happening in the first roll, those are all the, like, the individual probabilities of getting 9 pins down on the second roll.
Right. So there's really only 2 possibilities in this case. You could get 0 and 9, which is that. Or you could get 1 and 9, which is this. Together, they're 0.016-ish. There's more zeros over here, but adding 0 doesn't get you anywhere. And these are impossible. You can't get 2 on the first and 9 on the second. Illegal. So the only ones you actually have to worry about are those 2. And those 2 added together are the probability of knocking down 9 pins on the second roll, irrespective of the first. But when I say irrespective, it's not totally irrespective, because you have to see which possibilities on the first roll are compatible with 9 on the second. But then you add those up and you get the probability of 9. Question, Tim?
Wouldn't that just be the equation, like the intersection of having the 2 equals just PA is, actually never mind.
I don't think so.
Hang on.
It did not sound like you were on the track to a question that I would have answered yes. But
That myself.
if another question comes to you, be sure to raise it. All right? Everybody understand how we came up with probability of knocking down 9? Second roll, irrespective of the first roll. Irrespective pretty much just means sum over. All right? Okay, probability not exclusive events. How would you compute the probability of knocking down 8 pins on the first roll or 2 pins on the second roll of the same frame of bowling using the database of 10 million frames that we simulated the modern way? What dplyr syntax would you use to compute the probability of 8 on the first or 2 on the second in the same frame of bowling? Yeah?
Is it the same as before, just change the and to a or?
Pretty much, yeah. So we'll summarize the frames, calculate this probability of the average of x1 equal 8 or x2 equal 2. That is the right answer. One thing that you might think is the right answer, but is actually the wrong answer. Calculating the probability that x1 is 8 and then adding to that the probability that x2 is 2. And why does that not yield the right answer?
Because there's the outcome where it overlaps that you count twice and need to correct that.
Yeah, so this event here, the average x1 equal 8 includes x2 equal 2. And when you calculate it over here, what's the probability that x2 is 2? Well, that includes in it the possibility that x1 is 8. So the event 8 on the first and 2 on the second is being counted twice. Consequently, we could get the right answer again by doing that sum and then subtracting off the probability that x1 is 8 and x2 is 2 to avoid the double counting at the intersection. And that is a more complicated way of, again, arriving at the right answer, approximately 0.171. Okay. Ancient calculation. How would you calculate the probability of 8 on the first or 2 on the second using that 11 by 11 matrix?
You sum everything that's found on the row and the column.
Sum it like this. So that'd be the row. And then you want to add that sum.
And then of course you correct by moving the.
And then you want to subtract the one that got counted twice. So ancient calculation, take the sum of the 11 by 11 thing in row with the label 8, add to it the sum of the column with the label 2, and then subtract from that the probability of 8 on the first and 2 on the second to avoid the double counting. From this, come out with 0.171. Essentially the same as what we got with the database query modern way, doing it with simulations. Everybody see? So the double counting thing can be a little tricky. It's not tricky to account for, you just got to remember to account for it. Questions? Making good progress. So Aristotle again. We did this with the AND operation before. We can do it with the OR operator. So in R, the vertical bar means OR, not given. So true or false? True. False or true? True. False or false? False. And then true or true? True. If true maps to 1, false maps to 0, we can do it with addition. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. And then the last one's a little bit tricky. True plus true, well, that'd be 2. It's never good when your probability is 2. So you got to subtract the probability that both are true simultaneously. True times true. And 2 minus 1 is 1, which is extreme but valid for a probability. And we can generalize the Aristotle thing where things are just can only be true or false. We can generalize that to the probabilities, all the numbers between 0 and 1, using what is known as the general addition rule. So this giant U thing reads as OR. The probability that A or B happens is the probability that A happens plus the probability of B happens minus the probability that A and B both happen simultaneously to avoid the double counting that we got when we summed the first two things there. And in a special but reasonably common case, where both A and B can't be true simultaneously, their probability is 0, then A and B are said to be disjoint, and then you're just subtracting 0, so you could skip it. A and B are disjoint, otherwise known as mutually exclusive. Then the probability that one or the other happens, because both can't happen, is the sum of their respective probabilities. All right, so we got two rules: general multiplication rule, general addition rule, along with the, I mean, it's a rule, but it doesn't have a special name. Probability's got to be between 0 and 1, and they've got to sum to 1 over the entire input space, sample space, omega. In the case of bowling, would be 0 to the number of pins upright. We good? Okay, so like we said at the beginning, a random variable is a function. It's a function from omega to some subset of the real numbers with a probability-based rule. And consequently, if a random variable is a function of a random variable is another random variable. So a function of a function is a composite function. So a function of a random variable is another random variable. Random variables have the so-called viral property to them, which allows us to ask more advanced bowling questions, such as what is the probability of getting a spare, which is the event you knock down all 10 pins over both rolls of a frame of bowling, but not all 10 on the first roll. That would be a strike. How would you compute that using our Tibble database of 10 million frames we simulated and dplyr syntax?
Just do mean x1 plus x2 equals to 10 minus x1 equals to 10.
There's no minus.
Oh, sorry. Mean of that minus mean of x1 equals to 10.
Still no minus. But you're close. You do it like this. Pass the database to summarize. Compute spare probability as the proportion of times where x1 is not 10 and x1 and x2 together added are 10. So there's no subtraction operation here. Indeed, that would not yield the right answer. But this relatively simple one line of code does yield the probability of, at the outset of a frame, the bowler getting a spare. 0.317. So x1 is not 10 and x1 together added together are 10. That's the event. And we want to take the proportion of times that happens in our 10 million frames, 0.317 for the probability of a spare. And how would you calculate that exactly using the joint PR table that we constructed a while back? Deterministically, ancient style. Yeah?
Wouldn't you just sum all the probabilities? It's where the first row is not, the first column is not 0 and the last column is not 10.
So not this one.
Yeah, and not the upper right corner. You just sum all the probabilities on that diagonal.
Yeah, so this one over here is actually legal. 0 on the first and 10 on the second, that is a
So
spare.
you would sum all the ones that are not 10 comma 0.
Yes. That is how you would do it the ancient way.
So I correct clarify.
Oh, question?
For the line of code, if I wrote spare probably equals to mean x1 plus x2 equals to 10 in close bracket minus mean x1 equals to 10. Would that work in our code or would that not work?
No. Well, one thing that could work I guess. So I think actually I'm going to change my mind. What you said, I think, could be right. If you took the whole diagonal there and subtracted off this, that would be valid. Yes. I think an easier way to think about it is just don't touch this one and just add all those. But anyway, ancient way, initialize spare prob to 0, do a for loop where you increment spare prob by adding to it all the probabilities that yield to a spare. Again, I got a +1 the indices because it starts with 1 rather than 0. And because 9 and 1, 8 and 2, 7 and 3, those are mutually exclusive. I don't have to worry about subtracting off anything. I just add, yielding me a spare prob 0.3165. Exactly. When I say exactly, I mean as exactly as a finite computer can do. But you can just call that exactly for today. All right. Okay, so we did this a little before. If you want to know the probability of knocking down 8 pins on the first roll of a frame of bowling, you could just add those 3 together. You would get this over here, 0.116. And that's the same that you would get if you evaluated the PR function at 8 when n is equal to 10. Or more generally, you could get what we get when we evaluate the PR function by evaluating the row sum of this matrix. You get the numbers over here in the column called row sum. And these numbers over here are called marginal probabilities. Now, there's many things in statistics, this one included, where you hear a word and it doesn't mean what you think it means in English. So if you just say something is marginal in English, that means it's like not very important. Or if you say something is marginal in economics, you mean at the margin of the market. This sense of marginal probabilities is literally in the old days, they would write these numbers in the margin of the page. And so they came to be known as marginal probabilities, but they are actually really important as a way of aggregating over joint probabilities. And we can do the same things with the columns, except I can't move the mouse accurately enough. But if I take the sum down any of these columns, I get the number in the bottom margin, which is the probability of knocking down that number of pins on the second roll of the frame of bowling, irrespective of what happens on the first. So these are the marginal probabilities of x2. Over here with the row sum is the marginal probabilities of x1. Question?
Wouldn't it be more intuitive to call them, I don't know, unconditional probability, in the
Yes.
sense of unconditional expectations?
Unconditional would be a better word. Irrespective, like x2 irrespective of x1, x2 regardless of x1. Any of those would be better words than marginal. However, marginal is the one that you will see in the textbook because it's what everybody has been using since they were writing these numbers in the margin of a book. All right? So it's not that they're unimportant. They're very important. But they have a weird name. So we can check our database simulations again by counting up the number of times that x2 pins, all the number of times that those happen in our database. We can calculate the proportion as times divided by r, and the exact probabilities are given by the column sums of our joint PR 11 by 11 table. As we can see, the numbers are again very, very similar. So the proportions are not quite exact because 10 million is not quite infinite, but they're more than adequate. And we can see on the second roll of a frame of bowling, the most common, almost 40%, is 0. And then they get smaller from there. So the least likely thing to happen on the second roll of a frame of bowling is to knock down 10 pins, even though 10 was the most likely thing to happen on the first roll of a frame of bowling. So the x1 marginal probabilities are not the same as the x2 marginal probabilities. They're very different numbers, and they're very different concepts, but they can be obtained, one of them by summing the rows and the other by summing the columns of this, where all the numbers in black add up to 1. It's the joint probability of something happening on the frame is 1. All right. So I personally invented the notation probability of x1 and x2 with x1 crossed out to refer to the marginal or marginalized or unconditional probability that the random variable x2 is equal to a particular value little x2, irrespective of x1, regardless of x1. But despite this being the perfect notation, no one else uses it. So you will not see it in the books or the videos or like anywhere on the internet. So it's just me. I use this notation where if I want to marginalize over something, I cross it out, which is more consistent with what we're actually doing when we obtain these marginalized probabilities. But I think my way is better for learning because it makes more sense and it does not use the word marginal. All right, so to wrap up all the stuff that we've been building to compose a joint, in this case bivariate, but like I said, this generalizes to trivariate and 3, 4, 5, etc. fairly simply. You multiply a marginal probability of the first thing times the conditional probability of the other thing, given that the first thing happens. So to compose a bivariate probability, you multiply a marginal probability times a conditional probability. That is the general multiplication rule. Damn, my margins got messed up. General multiplication rule, multiply a marginal probability times the conditional probability given that the first thing happens to obtain the bivariate, otherwise known as joint, probability of both of those things happening. Where was it? I did that already. We've done a lot of stuff today. Here we go. Compose. Bivariate probability. Multiply a marginal probability times the conditional probability given that the first thing happens. And it still messed up my margins. To decompose a joint probability, you add the relevant joint probabilities to obtain a marginalized, unconditional, irrespective, regardless probability. And to obtain a conditional probability, you divide the joint probability of both things happening by the marginalized probability of what you're conditioning on, which I will write on the board because it got messed up in the slides. The bottom line here, probability A and B equal probability A times probability B given A, but that is also equal. Okay. That is also equal to the probability of B times the conditional probability of A given B. And since both of these things in the general multiplication rule are equal to the same thing, provided that the probability of B is not 0, I can write the probability of A given B as the probability of A times the conditional probability of B given A divided by the marginalized probability of B. But my notation for this is better. Probability of A and B with B crossed out. And that is Bayes' rule. So I wish it hadn't fucked up my margins. So I can obtain the conditional probability of A given B on the left-hand side here by evaluating the three terms on the right-hand side there. I can get the probability of A given B by evaluating the probability of A, the probability of B given A, and dividing by the marginalized probability of B. Right? So that's the third thing here. To obtain a conditional probability, divide the joint probability by the marginalized probability of the thing you're conditioning on. And the joint probability can be obtained by multiplying a marginal times the conditional. And the marginalized probability can be obtained by summing over the relevant joint probabilities to get the marginalized probability of the thing that you want to condition on. So, to be concrete about this, how would you compute the probability that x1 is 8 on the first roll of a frame of bowling and x2 is 2 on the, oh no, I said it wrong. Probability that 8 pins knocked down on the first roll of a frame of bowling, given that x2 pins were knocked down on the second roll of that frame of bowling. How would you compute that using our database of 10 million bowling frames and dplyr syntax? Condition on something in dplyr?
Yeah, filter.
Filter. So more specifically, I mean that's the right track, but explicitly?
You're filtering for cases where x2 equals 2.
Filter for cases where x2 equal 2, so I get a smaller database, a subset of the database where x2 is 2, and then I do what?
And then you do a mean x1 equals 8.
X1 is 8?
Yeah.
Yeah. So first I filter according to the condition that x2 is 2, get a smaller subset of my original database of bowling frames, and then in that I pipe it to summarize, and within that subset I compute the conditional probability as the proportion where x1 is 8 among just the rows where x2 was 2. And I get 0.512. Better than half chance that if x2 is 2, x1 being 8. And how would you calculate that the ancient way? Using our 11 by 11 table of joint probabilities for a frame of bowling? Ancient calculation? Albeit with a couple $1,000 computer? But mimicking the way of the ancients?
You look at the column for x equals 2, and then you take the value you have for the x1 equals 8, and then you divide that by the marginal probability for the column.
So I evaluate my joint probability at the 8-2 spot. the probability of knocking down 8 and 2, and divide by the marginalized probability of knocking down 2 pins on the second roll of a frame of bowling, which is the sum down the column labeled 2, and lo and behold, I get 0.511. So the probability of knocking down 8 pins on the first roll of a frame of bowling, given that 2 pins were knocked down on the second roll of that same frame of bowling, is about 0.5, a little bit more, as compared to the marginalized, or what we might say prior, probability of knocking down 8 pins on the first roll of a frame of bowling, irrespective of what happens on the second roll, which is only 0.116. So by telling you that 2 pins were knocked down on the second roll of this frame of bowling, you update your probability of 8 pins being knocked down on the first roll of a frame of bowling from 0.116, which it started out as, to 0.512. So conditioning on the fact that 2 pins were knocked down on the second roll of this frame of bowling allows you to drastically update your probability of 8 pins being knocked down on the first roll of that frame of bowling. And a little bit of intuition for that. Well, if I tell you 2 pins were knocked down on the second roll of this frame of bowling, okay, we're somewhere in this column here as to what happened. But 2 on the second roll precludes 9 or 10 on the first roll. Can't happen, according to the rules of bowling. But 9 and 10 were actually the 2 most popular probabilities marginally. They were 0.1632 and 0.279. But those didn't happen. So their probability has to get reallocated to the things that could have happened. And most of that reallocated probability goes on to 8. Indeed, it's in proportion to this, but divided by the marginal probability of knocking down 2 pins on the second roll, which was about 0.11 something. Yeah, 0.113. So I take this number here at the intersection of the 8 and the 2, and I divide it by the sum and 2. I come out with a number slightly greater than 0.5. A updated probability of knocking down 8 pins on the first roll, given that 2 pins. And it's much higher than the probability of knocking down 8 on the first, irrespective, regardless of the second roll. And that's Bayes' rule. Using Bayes' rule to get updated probabilities given the information we have available. And you might say, should say, well, if these ancient calculations yield essentially the same number as what we get for querying our database of 10 million bowling frames, then what could be so bad about a procedure that yields the right answer? Well, what I've done so far, the example with bowling in my database of 10 million bowling frames, is actually consistent with the frequentist view. And that can get a little bit confusing, so let's be explicit about it. Bayesians generalize this formula that I wrote on the board there, probability of A given B. So this is the correct version of that. So A and B, A given B here. So they generalize the interpretation of this by taking A to be whatever you don't know, and taking B to be whatever you do know. So according to Bayes' rule, if A is whatever you don't know and B is whatever you do know, the probability of whatever you don't know given whatever you do know, can be computed by evaluating the right-hand side here. Marginal probability of A, conditional probability of B given A, marginal probability of B, which is probability of A and B with A crossed out. But utilizing Bayes' rule, it's a necessary but not sufficient condition to be Bayesian. And whereas what we did previously is fairly consistent with the frequentist view, but frequentist, Bayes' rule is a fairly trivial consequence of the general multiplication rule. There's nothing really to object there mathematically, but frequentists do, or at least have, strenuously objected to using the language of probability to describe your beliefs about unknown propositions, such as A, insisting that probability of a process be defined narrowly as the limit of this ratio. The number of times that A occurs in R independent randomizations divided by R, the limit of that is R approaches infinity, is the definition of the probability of A happening. And if you conditioned on it B, then it would be the number of times that A occurs in R independent randomizations when B is true, divided by the number of times where B is true, etc. But the point is, frequentists insist that probability only applies to things that have been randomized. And so in our database of bowling frames, that was okay. We did randomize X1 and we randomized X2 conditional on X1. And, we did that with 10 million, which is, pretty close to the limit as R goes to infinity. So all that's fine. The math behind Bayes' rule is fine. What old school frequentists do not like is the fact Bayesians took an expansive interpretation of Bayes' rule to where A can be whatever you don't know, irrespective of whether it's a random variable, whether it's been randomized, and then B, whatever you do know. And so the Bayesian interpretation of Bayes' rule is, my beliefs about the probability of A happening given that B has happened. But beliefs are not a random variable. They're just describing what you believe using the tools of probability. And according to frequentists, that is a perversion of probability. So another way to think about this, which is a nice example that John Cook came up with, asks the question, what is the probability that X is a prime number if X is some odd integer like 1 plus 10 to the real big exponent? So from a frequentist perspective, the number X is not a random variable. It's just a number. It's either a prime number or it's not a prime number, otherwise known as a composite number. So it makes no sense to say X is probably. There's no way you can end that sentence from a frequentist perspective that would make any sense at all, because X is not a random variable. It would be like saying, what's the probability that pi is 7? It just isn't. So from the frequentist perspective, it gets back to this Aristotelian Boolean view of things, where stuff is either true or false. And if you don't randomize it, then you don't have a random variable. And if you don't randomize stuff, then you don't have this ratio here that you can take the limit of to yield a probability. So you might not know if X is a prime number, but it either is or it isn't. It's not probably anything. Yes?
How do you account for like confidence intervals with the
Right.
frequentist approach?
So we'll get into that a little bit, but it's a great question. So confidence intervals refer to the random variable that is the estimator The thing that you're estimating, like some population parameter, is not a random variable. In which case, it's not correct to say beta is probably within here and there, because beta is not a random variable. And so it either is between here and there, or it isn't. Everything is either true or false. But what is a random variable is the estimator, because the data that you sample from the population is a random variable. Any function you apply to a random sample is a random variable from a frequentist perspective. So the endpoints of your confidence intervals are random variables. And so you can coherently say from a frequentist perspective, if we did the study over and over each time with a different random sample, we get all these different confidence intervals. And the proportion that would include the fixed true unknown population parameter is 0.9 or 0.95, depending on what kind of confidence interval it is. But the point, which is nicely illustrated by that question, is you only use probability to describe random variables, things that were explicitly randomized. And so if you explicitly randomize who's in your sample, you're good. If you want to apply some function to a random sample, you're good. You got random variables. But if we're talking about a number x, 1 plus 10 to the 100,000, it's not a random variable. I think I randomized. It's just a number. It is prime or it's not prime. It's not probably prime or it's not probably not prime. It's not probably anything because it's not a random variable. From a Bayesian perspective, well, no one knows for sure whether this is prime or not. It's way bigger than the biggest known prime number. But you could choose and then update some prior probability based on its number of digits. So a famous mathematician has figured out that the probability that some number is prime, given that it has d digits, is equal to 1 over d times log 10, which in this case would be approximately a really small number. So from a Bayesian perspective, it's totally fine to say this number is probably not prime, because it's real big. There's lots of things that might divide it cleanly. Okay, so we start off with the initial probability that x is prime, given that it has like a zillion digits, is some 10 to the 10, 1 over 10 to the 10 business. But you might look at this number and say, that's an odd number, and the even numbers aren't prime, except for 2, which that is not. So the probability that x is prime, given that it has d digits and is odd, is twice this. And so from a frequentist perspective, that's just crazy talk. How could the probability of x being prime double? It didn't change. Your mind changed. And that's the difference between the Bayesian perspective on probability and the frequentist perspective on probability. To frequentist, probability is a property of an object, or a random variable object. To Bayesians, probability refers to what's going on in your head. Your beliefs about whether x is prime. Well, it's probably not, because it's really big, but it's odd. So it's double this. 3 doesn't divide that. So the probability is prime goes up a little bit. 5 doesn't divide that. So the probability goes up a little bit. I don't know about 7, but the probability goes up and up as you ascertain more information that you can condition on about it. And if you discover some prime number that divides that cleanly, then the probability that x is prime goes to 0. It goes down. But these are all referring to changing your mind. Nothing about x is changing. Anusha.
So a general thinking of Bayesian is basically like they don't rely as much on randomization. So like nothing is basically a random event then in this case, because we rely on our beliefs. Is that what I'm kind of understanding?
Yeah. Bayesians are using probability to describe unknowns. It's a method of communication articulating what's going on in your head. It's a property of the subject rather than a property of the object. And that's what frequentists object to in the strongest possible terms. And so you might say, well, I don't care whether X is prime or composite. I've never encountered a number that big. Why does it matter? And so then I would ask you the question, what is the probability that beta is positive in some regression model? But that's really the same question. To frequentists, positivity of a number is a property of an object. And since beta is not a random variable, it's just some scalar, we don't know it, but it's not being randomized by anything, so probability doesn't apply to it. Thus, it makes absolutely no sense from a frequentist perspective to say that beta is probably positive. But from a Bayesian perspective, we could have a prior probability that we think beta is positive before we see the data. We could update that, get an updated probability that this is positive, and thus, from a Bayesian perspective, it's entirely coherent to say the treatment, estimated treatment, is probably beneficial. And not just like it probably is, we can say the probability that it's positive is 0.512 or something that we can calculate literally with Bayes' rule or simulations thereof. Which brings me to the video on the syllabus for today by Grant Sanderson, where he gets to talking about the scope of Bayes' rule, and Steve, who might be a farmer or librarian, whatever. And so we're using Bayes' rule to calculate the probability some hypothesis is true given the evidence. H is hypothesis, E is evidence, otherwise known as data. So in the bowling example, the hypothesis was that 8 pins were knocked down on the first roll of a frame of bowling. The evidence, the data, was 2 pins were knocked down on the second roll of that frame of bowling. We computed the updated probability 8 were knocked down on the first roll given the 2 were the second, and that was 0.51-ish rather than 0.115, so we updated that. And Grant says in the video, what's noteworthy, there's such a straightforward fact about proportions, Bayes' rule, can be hugely significant for science, AI, and any situation in which you want to quantify belief. And so Bayesians would say, well, probability the hypothesis is true given the evidence is the essence of science. Everything about science, whether it's academic research or otherwise, is either that or building up to that. And Fisher, which is sort of the chief frequentist 100 years ago, argued otherwise. Said the theory of inverse probability, which is what he called Bayesian back then, is founded on an error. It's treating things that are not random variables as if they were, and must be wholly rejected. So the hypothesis is not a random variable. The prior probability the hypothesis is true is not a random variable. The marginalized probability is not a random variable, and the posterior probability is not a random variable. So this use of Bayes' rule to say the probability the hypothesis is true given the evidence makes no sense, or else is just the subjective beliefs of the researcher, and science should be more than what any individual believes. Science, according to Fisher, is getting at what's true and what's false, not what somebody believes is true or false. And so frequentism is set up to be all about hinging on the probability, the evidence, because the evidence may be a random variable, is true given that the hypothesis is true. Which from a Bayesian perspective is exactly backwards if what the scientist wants to know is what's the probability the hypothesis is true given the evidence. And so we can see, or at least 100 years ago, the disagreement between Fisher and the few Bayesians that were around back then is a disagreement about whether science should be objective in Fisher's sort of warped sense, or should it be what scientists want to know? And then supervised learning just, it accepts the base rule as fine, but doesn't really use probability all that extensively. Quick question?
In that case, is there a meaningful difference between p-values and likelihoods?
No. Well, they're both based on the same, from a Bayesian perspective, backwards looking thing. Alright. Other questions real fast? Okay, out of time. See you next week. Check your email. We will be having another recitation session to go over the material that we zipped through today. Not quite sure what time that will be, but we'll let you know. And it'll be on Zoom if you can't make it in person. If you have any questions, feel free to ask them on Ed Discussion. And all this will be updated on the GitHub repository as soon as I get back to my lab.
The recitation's recorded.
Yes.